So we're digging a little bit deeper into this whole idea of atomic and electronic configurations, and just what the electrons are doing in regards to their energy and interactions. I thought this is kind of neat. It's about as famous as a physicist can get, Richard Feynman. He kind of puts things in a way that people could kind of relate to, this really abstract stuff. And he said that if there's one thing that you could pass on, I don't know, there's going to be a nuclear war, all of our knowledge is going to disappear, and you can just pass on one idea. And he said this is what he thinks would be the most useful, that everything's made of atoms. Little particles that move around in perpetual motion, attracting each other when they're just a little distance apart, but repelling when you squeeze them into one another. So out of that one idea, comes a lot of information. So that's kind of the basis of a lot of our current technology. Now that doesn't mean that we understand everything, and we don't. We've got a ways to go, but it's a fundamental idea. So on that trend there, we're going to start with talking about some trends from the periodic table and kind of using the periodic table as a cheat sheet. So start with the atomic radius trend. Paul, you've got a lot to pick from. I think 114 elements up there. What would you guess is the biggest element that's up there? 1 out of 114 chance. Yeah. Does anybody know what the biggest element is? I mean, the atom. You have one atom of this stuff, and yeah, they're almost all atoms are pretty much all empty space. But you've got that hard core nucleus. It's kind of like the Alamo Dome. Throw an orange on the 50-yard line, there's your nucleus. And the electrons are taking up the entire rest of the dome. So it's almost all empty space. But the biggest atom up there starts with an F. It's Fr. Francium. Francium's the biggest one. Okay, the smallest, because we're supposed to draw an arrow. I guess we should answer this, right? We're supposed to draw an arrow from the smallest to largest. So we better end up at francium. But what's the smallest? Yeah, it's helium. So we'll start at helium, good, and then we'll just draw it out all the way down to francium. See if you can draw a diagonal line like that. Not too straight, but that's the idea, right? From smallest to biggest. Electrons in the outer lying atomic orbitals feel. They feel, Stephen, an effective nuclear charge. Now, electrons have what charge, Stephen? Electrons are negative, and that nucleus, Steph, is what? Positive. So that's what they're talking about, the feel, that pull, right? So Giselle, electrons in the outer lying atomic orbitals feel an effective nuclear charge that is blank.
Would it be less than?
It's less than, right? And there's a couple reasons. One is that they're simply farther apart. I mean, they're farther away, right? But that's really not the main reason, because these things are so tiny in the first place, right? And that charge is so concentrated in such a small particle. The real reason is that electron way out here, he's got a lot of other electrons between him and the nucleus, right? So that's really what's doing the shielding. It's really making it feel less. Ionization energy. I already picked on Lauren. What was an ion? I say, this is an ion. What's an ion? Does anyone help her? What's an ion? Kenneth, what's an ion?
Wasn't it an atom of an element with a charge?
Yes, something with a charge. So we got a lot of ions. Remember, we memorized chloride, we had polyatomic ions, phosphate, sulfate. We had oxide, O negative 2. We had sodium ion, Na plus. All those guys, ions. Good. An element with a charge. So it either has too many or not enough electrons, essentially, right? So if I'm going to ionize something, Mia, would it take energy or would it absorb energy? if I'm going to ionize something. Now, realize what you got to do, though, to make an ion. Right? Now, I guess you're right. You are right if we go the other way. What I'm thinking of in my mind is the positive ions. It starts with a what? How do you say positive ions? We had negative ions, positive ions. They were called cations and anions. Yeah, so making a cation is I was thinking, right? Because if you have a cation, you want to make something positive. So you have to pull a what away from it? An electron. Electron has what charge, everybody? Negative, right? Nucleus is positive, so it's going to suck up energy to do it. That's what ionization energy is. The energy to pull an electron away. Okay? And I added this just to make sure we can see what the heck we're doing. Write an example of an atomic ionization reaction for sodium. So sodium was Na. So all I want to do is just give it a whole lot of energy, well, the ionization energy. Right? Probably blast it with the right wavelength of light, and then I'll get an electron, and what? Megan, what would I get? Na positive, right? Na positive. That's the idea, okay? Sketch an arrow. Now we're sketching another arrow on ionization energy trends. Sketch an arrow from the smallest to the largest ionization energy. The element that's the easiest to ionize to the element that's the most difficult. Lorena, do you think that might have something to do with size? Right? Because if you have a huge atom, that atom is so big because the electrons are just flopping around out there. They're hardly even attached because it's so big, like francium. Then you've got helium. It's compact as a rock, right? I mean, it's still mostly empty space, but the idea is that it's really compact. It's much more dense. It's much smaller. Shouldn't they have different ionization energies? Steph? Right? Which one would have a higher ionization energy? Which one would it take more energy to pull an electron out of there? The smaller one, exactly. So if you can remember that, if you think of it that way and understand it that way, you just draw an opposite trend line that we did for size, right? So before we said that francium was the biggest, right? We said that francium was the biggest, helium was the smallest, and our trend line went pointing to francium. Well, now we're supposed to point the trend line, have it point towards the largest ionization energy. Well, it should point towards what then? Helium. Yeah, so have it point up there and start at francium. If you can draw straight, that's better. Okay. Electron affinity. This is where Mia threw me a curveball. I don't think she realized it. Okay. Electron affinity. Bowdy, this is an odd idea, and I don't even know if there's even any homework on this. Ionization energy was losing electron. What more than likely is electron affinity? Gaining electron. That's all it really is. So write an example of electron affinity reaction for chlorine. So I have a chlorine. I'm supposed to add a what to it, Connor? What would be the other reactant? I have chlorine, and the other reactant would be a electron. A little E negative. And then everybody I'd end up with Cl minus. Yeah. So that's the idea there. Sketch an arrow from smallest to largest electron affinity. And that just goes straight across, but it stops at the nobles. So you recognize this box here on the periodic table? That's the noble gases. That's group 8. All right, that's group 8. So the arrow just goes straight across, and it stops at the nobles. So the halogens have the highest electron affinity there as you go across a period. Okay. Now this word, electron affinity, you don't hear that too much. But coming up in a lot of topics, especially in Gen Chem 2, you're going to hear this word a lot. This word you hear a lot, electronegativity. It's much more useful, I think, Emily, from a chemistry perspective and reactions and how things interact with each other, different molecules, how they interact. What's electronegativity? Now, let's back up a little bit. What type of compounds actually had molecules? You know, they could be, if you're making them a gas, they could be flying around. Was it molecular or ionic compounds? Do you remember this? It was way back many, many weeks ago. Now, ionic, ions held it together, and they were all crystals. And you had to have a what? Metal. Okay. And then the molecular compounds, remember to name them? You had to count to 10 in Greek, right? Like carbon tetrachloride, that kind of thing. So the molecular compounds were the ones that we counted to 10 in Greek. So let's say you had something like carbon tetrachloride, right? So you have a whole bunch of molecular compounds, and there's just no metal. Okay, so the reason why I'm going through all this is because if you try to start drawing out these molecules, right, they're held together by these bonds, and you're supposed to be sharing electrons, right, that sort of thing. But it's not that simple. I mean, electrons, they're going to hang out by certain elements more often than the other elements. And that's just life. I mean, and look at it. What group of elements on the periodic table is supposed to be the most stable?
The noble gases.
The noble gases. Okay, so look at it. I mean, if these guys really close to the noble gases, they are going to really want electrons, because all they need is one more. These guys could care less. In fact, they don't really want to, look how many electrons they'd have to gain. Instead, they would just, like especially this group, just lose how many? One. And then they'd have the same noble gas core, electron configuration of nobles. That's all that we're talking about. And that's all really electronegativity is this trend, this somehow that in nature certain elements are just closer to the nobles and they want that electronic configuration to be stable. Balls roll down hills. Chemistry, things want to get to the noble gas core notation. That's the bottom of the hill. That's where everything, nature is always trying to do that. Nature never has a ball roll up a hill. Everything's always trying to reach lowest energy. So this is how it gets there. Okay, and this propagates through, this idea of electronegativity propagates through chemical properties, reactions. It's just in a lot of places that we're going to see. So it's a big deal. So electronegativity, right? What could you say? The ability or the tendency or the desire or the strength of an element to pull in more electrons towards itself. It just wants more electrons. So which element would you guess is the most electronegative, Ashley? What would you guess, looking at the periodic table? Fluorine. Yeah, pretty much all the halogens, all really electronegative. But fluorine is the worst. Because look, he's so close to helium. So fluorine is the most electronegative. So the least electronegative is going to be the biggest guy, francium, right? So we'll kind of, again, we have to draw our line here and stop at fluorine. Oh, I have such a hard time drawing straight lines. All right, end up at fluorine. Okay. Isoelectronic. Kenneth, this is a concept that can be kind of confusing, but once you get the idea of the rules of the game, it's not so bad. What is isoelectronic? It means, does anybody know? Iso means one. One electronic configuration. Remember it makes me think of that stinking movie, One Ring to Rule 'Em All, right? But anyway, one electronic configuration. So let's, I don't know, Manuel, give me any element. Name any element up there. Lithium, Li. Okay, lithium has some type of electronic configuration. We could write it, right? Beryllium has a different electronic configuration. But what if I wrote Be plus 1 or Be minus 1 would give me the exact same electron configuration as lithium? Now, Be is not the same. But Be with what charge would be? Minus 1? So right now, beryllium has 4 electrons. If you say minus 1, how many electrons would you have? Not 4 anymore, but 5. You have to add an electron. So that won't work. Lithium has how many electrons? 3. So that's really the key, is find anything with 3 electrons. Well, beryllium, not minus 1, but plus 1. That would have the same electron configuration. You're not supposed to say same electron configuration. You're supposed to say they are isoelectronic. How about, let's pick, I don't know, oxygen. What could you do to oxygen to make it isoelectronic with lithium? One, two, three. How many? Right? Now you can count. I'm sitting there sitting, and I lose count. It's a lot easier just to subtract, right? Because O is 8, lithium is 3. 8 minus 3 is 5, so lose 5 electrons. Well, you can count the boxes too. O all the way down until you hit lithium, that's 5 boxes. You have to lose 5 electrons. So that would be O plus 5. That's how you play the isoelectronic game. But this doesn't happen because oxygen does not want to go to lithium. Oxygen wants to go to where it's the most stable. And what's the most stable, Mia, electron configuration? The nobles. So oxygen doesn't want to lose electron. It wants to gain everybody how many? 2. That's why we wrote O negative 2 all the time, oxide. It didn't form O negative 1 or O positive anything. It was O negative 2 every single time. We call that oxide. So all these atomic ions of groups 1, the alkali, groups 2, the alkaline earth, and group 7 are isoelectronic with a blank blank. These ions. So group 1, that'd be like sodium ion. Group 2, what's something in group 2? Calcium. The ion it formed. Group 7, oh, like bromine. These are all isoelectronic with a what, Dylan? With a, starts with an N, noble gas. Right? So you look at the periodic table, clean this up a little bit, right? All those halogens, they just need 1 electron. So that's why they're all negative 1, right? All these guys have negative 1 charge. These guys all here lose an electron. So they're all positive 1. All these lose 2 electrons. They're all positive 2, right? So then it'll be isoelectronic with a noble gas. All righty, so look at that. Just do 4 or 5 problems here. Write our answers on the boards, and we'll be out of here. This might be a short day. Okay? So write your answers on the boards. They'll be quicker. Then everyone can look at Megan's answer and just copy it.
What if I write really small?
So write the neutral element that is isoelectronic with each. So for A, B, and C, write the neutral element that is isoelectronic with each. A, B, and C. Just write A, B, C, and then write your answers. See if everybody agrees. Hmm? No, I just want you to name the element, or give the formula for it. The chemical formula. Like magnesium, it's either going to be 1, 2 silicon, or it's going to be 1, 2 neon. It's magnesium. If it was magnesium minus 2, it'd be silicon, right? Because magnesium, yeah, because it has to lose 2 electrons. Good, so it has to be neon. Neon would be the first one. So you have to lose 2 electrons. So it just wants a neutral element, so you got to move them around. Yeah, I know it's weird. S minus 2, you think you want to subtract electrons, but no, you got to give it 2 extra. Right? So find S. See, Paul, you find S and you just give it 2 extra. 1, 2. So everyone agree? S minus 2 is argon. And iron 3 is? So we want to lose electrons. So we don't want 26 anymore, and you want 23. So look at 23, and that's 1, 2, 3. Vanadium, right? Make sense? And then order the elements in order of first increasing size, then ionization energy. This homework's not going to be too bad. Right, Connor? You're going to fly through this. So just remember the trends. Remember how size went. Biggest element, smallest element. Everybody agree? F, P, M, G, S, R. I think everyone's got, well, you already erased A, all right? I think most everyone has this, right? Well, fluorine, because you want to end up with whoever's closest to FR being last, all right? And I think magnesium is closest to francium. Okay. And then ionization energy, remember the arrow is just the exact opposite, so just flip your order, and you'll have the answer for B. Just flip the order, because it's the exact opposite trend. Okay, now there are some trick questions, so that's what's coming up with the next two. See if you can figure these out. These are more conceptual than they are. This really won't work knowing a trend on the periodic table. This is more of a conceptual question. 3 and 4 are. increasing size. A lot of folks have 2F C plus. You guys don't have anything written over here. You guys, what do you think? Now remember, what makes up size? The electrons. That's exactly it. So whoever has the most electrons is going to be the biggest. So what would be the biggest? It would be, you said it, Lorena? Carbon. Yeah, because he has the most electrons. Carbon would be the biggest. So I would list carbon last. All right. First should be C plus 4, and then you just increase the charge. Or sorry, decrease it. And then for ionization energy, just do what to the list you wrote in A? Flip it, because it's opposite. It's going to be toughest to pull an electron from C plus 4, because it has a positive 4 charge. Then do the same thing for the same type of thinking for number 4. So who would you say is the biggest out of these in number 4? Cl minus. Why? Most electrons. Yeah. And it's negative. All right, so those electrons are going to be repelling each other. It's going to be way out there. So make that the biggest. What would be the small? What would be the smallest? Cl plus. Good. And then just flip it. All right. Especially plus would be last because you have to pull an electron from something that's positive. That's tough. Okay, last one. Write the neutral element and its corresponding electron configuration using noble gas core notation. That is isoelectronic with each. Okay. So not only write the neutral element, but give its noble gas core electron configuration for each. So Br minus, to get you started, Br minus 1 is just going to be what? Kr in brackets, right? Because that's that noble gas core notation. So this isn't so bad, right? Kr in brackets, you can do that.
It's the noble gas, you just put it in brackets.
So they want the neutral element. Neutral element is Kr. Whoop. And then it's electron configuration. So both. It wants both for every question. The neutral element and the noble gas core notation. So if I lost you, just ask. So Kenneth, what did you write for calcium? The calcium ion.
If you get to a noble gas, like if you just go straight to a noble gas, you don't write anything else, or just...
Well, because this is the same as that, but this is not using noble gas core notation because you're full. So it's really argon.
Okay, so you just... Oh, okay, if it's noble gas, you just save it. Well, I got argon.
Yeah. Argon. Aluminum. Neon. Whoop. Oxide. Man, these aren't so bad, are they? Cadmium. Where the heck is cadmium? Okay, cadmium's going to be a job. So that one you got to figure out. And manganese is going to be a job too. Okay. See if you can E and F. What did you write for E and F? Did you get that? Get that far? Let's talk about E first. Cadmium. Cadmium is number 48, right? So what neutral element is isoelectronic with cadmium plus 2? What would you say? PD, palladium, exactly. Because you just look at the number pretty much. That's the easy way. 48, so I got to remove 2, that's 46. So find whoever's 46. So the answer is PD. Okay, and then you have to write its noble gas core notation for palladium. Okay. So what did you write? What's the noble gas core? Krypton. Then what did you write? Connor, what did you write after that? 5s2, 4d8. Does that make sense? Okay. Oh, but don't go on so quick, though. Remember, don't forget what we did last Friday. This is perfect. 5s2, 4d8. Remember what you're always supposed to try to make? 5 or a 10 for the D's. So can you make a D10? Yes, so you have to. You absolutely have to. That's why cadmium only loses 2 electrons, because then it gets this pseudo noble gas core notation. So how do I fix this? All right, krypton in brackets, then what? 4d10. You can write 5s0 if you want, but the point is 4d10. Play the same game for manganese 2. So what'd you get for manganese 2? Argon in brackets. Or what's the element first? Vanadium. Okay, vanadium. And it's argon in brackets. And then what did you say? 4s0, 3d5. Does everybody agree? Yeah, see? You're going to fly in this homework, right? Go home and do it right now, and then you'll be done. So have a good day.